Good afternoon, everyone. Thank you for joining this technical webinar. Today we are very honored at Diana FEA to have a guest lecturer, Dr. Arezou Fezolabegui. She's a strong expert in the field of historic building restoration and preservation. So we are very honored to have her as a guest lecturer today. And she's going to discuss the seismic assessment of dome structures with a special focus on an Iranian dome, the dome from Soltaniyeh, I hope the pronunciation is correct, which is a UNESCO World Heritage property. So we are very interesting to hear the outcome of her work that she has done in collaboration with the University of Minho. Before I pass the stage to Dr. Arezou Fezolabegui, I just want to let you know that during the whole presentation, your microphone will remain muted to avoid any background noise disturbances. But you have the possibility to type your questions. There is a question dialog box where you can type your question, and I will keep an eye on the questions. And if they are relevant for the audience, I will address them to Arezou at the end of the presentation. This webinar will be recorded, and after some post-processing work, within a few days, it will be available on our YouTube channel as usual. So, having said that, please welcome with me Dr. Arezou Fezolabegui. So, Arezou, if you can unmute yourself, the stage is all yours from now.
Hello, everybody. I would like to offer a warm welcome to everybody attending this technical webinar and say hello to those who will watch this webinar in the future. I would also like to thank Diana and Jean for providing this opportunity. Moreover, I would like to thank Dr. Rafael Ramirez and Professor Paulo Lourenço from University of Minho in Portugal for their contribution in this work. The topic of this technical webinar is the seismic assessment of dome structures with secondary structure elements such as minarets, and case study is the Soltaniyeh Dome in Iran. Okay. I will start with an introduction to introduce Soltaniyeh Dome. Next, a brief on methodology of the work, and next, damage survey and interventions, preparation of the numerical models, seismic analysis, including pushover analysis, and conclusion and future works are the next steps. One of Iran's most fascinating heritage buildings is the Dome of Soltaniyeh, which is located in the east of the country in Zanjan province and in an extensive archaeological site. According to the archaeological evidences, the site of Soltaniyeh was occupied at least from the first millennium BC as the ancient capital of the Ilkhanid dynasty. Soltaniyeh represents an exceptional testimony to the history of the 13th and 14th century in Iran. Being centrally located, the structure stands out in the city as the sole remains of the ancient kingdom. The central monument here of Soltaniyeh was the mausoleum for Ilkhanid Oljaitu, the king. The mausoleum was covered by a massive brick dome, which soon gave its name to the whole building. The monument is known today as the Gumbad Soltaniyeh in Persian, Dome of Soltaniyeh in English, which translates to the Imperial Dome. The building possesses several distinctive features that categorize it as a unique masterpiece of Iranian architecture. Notably, the double shell dome of the structure presents a particular dome construction technique in which the two shells, which are parallel, are connected through a network of ribs, as you can see in this picture. Furthermore, the dome is surrounded by 8 minarets, as you can see here. Each of these minarets has 2.5 meter diameter at base and an original height of 15 meters. The interior space of the building is composed of different sections, and its most remarkable aspect is its intricate ornamentations, as you can see here, which encompasses 10,000 meters square of different types of decorations. The Dome of Soltaniyeh was registered in UNESCO's World Heritage List in 2005. The building includes 4 levels, as you can see in this picture. The first and second levels include the dome hall and the tomb, the purple part. The third level includes the gallery and the rooms, which are here or here in the section. And the fourth level includes the terrace, dome, and minarets, which can be here. The building has 11 staircases, 8 of which start from the first floor and continue inside the minarets. As you can see, these staircases in the corners of this octagon. And 3 stairs emerge at the ground level here, the blue circles, and go up up to the second floor. The Dome of Santa Maria del Fiore in Florence is the most similar example to the Dome of Soltaniyeh, built 1 century later. Professor Piero Sampaolesi, in his book, suggests that the Dome of Santa Maria del Fiore, with its use of double shell structure, may have been inspired by the Dome of Soltaniyeh. You can refer to this book to know more about the similarities between these two. As brief, the methodology of this work includes a deep literature review, followed by exploration of the geographical context, then historical and damage survey, preparation of 3 distinct 3D FEM model, seismic analysis, and conclusions and some suggestions for future work. The main objective of this work is to contribute to the understanding of the structural behavior of massive dome structures and the effect of additional structural components that these domes have. Soltaniyeh is located in a high seismic hazard zone, having experienced several strong earthquakes over the centuries. Additionally, the building has undergone significant damages, notably the partial or total collapse of minarets that you can see in these pictures. In 1970s, extensive structural interventions were performed on the building by collaboration of Iran National University and ISMEO. You can see in this picture some of these actually interventions. These interventions and restoration works were not completed due to the 1979 revolution in the country. Fortunately, most major damages, specifically those involving the dome, have been addressed through restoration works. However, the minarets still present severe problems, requiring intervention works. Today, the most important damage observed is the partial and total collapse of the minarets. As you can see, minaret number 1, 2, 3, and 7 are original, but partially collapsed. Minaret number 4 is partially rebuilt. You can see here up to this part, it's original, but the rest have been rebuilt. Minaret numbers 5, 6, and 8, these three, have been totally rebuilt. As you can see, a concrete ring was added at the base of the dome in 1970s. Also, minaret number 2 here in this picture was strengthened with steel elements, cables, and cements. The most challenging part of this work was the modeling process. There is a huge scaffolding inside the building, as you can see in this picture, in the dome hall since 1970s, which was placed during the works of Ismail. The exterior part of the building and the site has been documented by means of laser scanners, photogrammetry, and other technologies. And the drawings are available, and you can see an example here. But regarding the interior part, due to the presence of these scaffoldings, the interior part is not accessible to prepare the drawings with instruments and have the accurate drawings. So it was done by tape measures. The next challenge was the complexity of the building. As you can see, the building the structure is very huge with 48 meters of height, and the span for the dome is 26 meters. And the thickness of the walls here, the main walls of the octagonal part and the dome hall, is 7 meters, and it has 3 levels of arches with different spans and heights. Also rooms in second floor and the gallery level and interior spaces. And complex walls of the gallery, which you can see here, these walls belongs to this part of which is the gallery. Spiral stairs, dome, and the pendentives in the tomb are the most complex parts to be modeled. All these made the modeling process very timing and challenging. Any small inconsistencies in the 3D model could cause severe problems in the finite element model. So we had to be more accurate, and we made several trials to reach to the final 3D model. To assess the seismic performance of the mausoleum, Diana software was selected to prepare the finite element models and perform the analysis. Since the objective of this work was to assess the seismic performance of the mausoleum and the effects of minarets as secondary structure elements, 3 scenarios were defined, and 3 finite element models were created based on the scenarios. The first scenario, you can see in the left picture, this model seeks to simulate the behavior of the mausoleum in its original configuration. So you see the full model with the minarets in full. In the second model, to study the effects of the minarets, all minarets were removed. And finally, in the third model and third scenario, which tries to study the effects of the minarets and the structure in the current condition of it. So the third model investigates the behavior of present situation of the building, including the interventions. Due to the large size of the model and its inherent complexities, and in order to decrease the number of the elements in the finite element model, that also affects the time of the analysis and time of the analysis, the simplification strategy was followed. So some assumptions were made, including the double shell box dome was considered as a single shell massive dome. In the current configuration model, the concrete ring and the minaret number 2, which had been consolidated, were considered with full linear elastic behavior. The connections between the walls in the models presumed to be perfect. The entire model is composed of solid elements meshed according to the element size. The spiral stairs were placed with cylinders with equivalent mass. For the simplification, we first tried to simplify this spiral stairs to this form of ramps, but again, there was several difficulties in the FEM model. So finally, we decided to replace the stairs with equivalent cylinders, as you can see here. In terms of material properties, 3 types of materials were defined. Material number 1, which you can see in this table, adapted to the whole masonry with these characteristics that you can see. Material type 2, adapted to the stairs. The properties of material type 2 were calculated considering the volume fraction, that is by multiplying the corresponding values of the masonry by the relation between the volume of the original spiral stairs and the equivalent cylindrical elements. In other words, material 2 was estimated based on the values of material 1 multiplied by a factor of 0.3. And finally, material 3 adapted to the ring and minaret number 2, which represents a linear elastic behavior. The nonlinear behavior of masonry was simulated using the total strain rotating crack model implemented in Diana. For the element type, element TE12L, which is a 4-node tetrahedron solid element, was selected. The element size varies from 15 centimeters for minarets to 50 centimeters for the rest of the structure. And here you can see the finite element model with mesh in Diana. And here you can see the number of elements in the all three models that we have, which range between 1 to 2 millions approximately. Due to the sensitivity and accuracy in Diana, it was very difficult to achieve the FEM model with such refined mesh, and the 3D model was modified for several times. In order to optimize the number of elements of the model, mesh refinement was carried out automatically and manually. This process considered crucial aspects for accurate numerical model, such as the number of the elements along the thickness of the structural element and overall mesh optimization. In the framework of this research, only vertical gravitational load or self-weight and the seismic load with horizontal pattern proportional to the mass of the structure defined by Eurocode 8 was adopted. In order to define the boundary condition, the translation of the structure in all directions assumed as fixed. In order to understand the damage condition of the structure and evaluate its stability, a nonlinear analysis for incremental gravitational loading was conducted. The first load step considered the total self-weight of the structure. In the subsequent step, the gravity load was incrementally applied to the structure to assess the vertical loading capacity of the building. Iterative method of Newton-Raphson was selected with convergence norms of force and displacement, and in case of difficulties in reaching convergence, the method was switched to secant method. To control and evaluate the displacement throughout the analysis, reference points were established, namely a control point on top of the dome, as you can see here, and a node on top of minaret number 7. Here in this picture, the graph illustrates the capacity curve of the structure, which can reach up to 5 times of the self-weight of the structure, which means safety factor of 5. The vertical displacement for the maximum load factor for the control point on top of the dome, as you can see, is almost 50 millimeter or 5 centimeters, whereas the control point on top of minaret number 7 experiences a vertical displacement of 32 millimeters. The distribution of maximum compressive stresses at the end of capacity curve in this picture presents high compression values concentrated at the base of the structure, particularly along the edges of the dome hull. Also, we can see the high compressions over the top part of the main arches inside the structure, which can see in these parts. The maximum principal stress as a damage indicator were used to evaluate crack pattern and collapse mechanism in Diana. As illustrated in this picture, the damage is more pronounced at the gallery level here, characterized by diagonal and horizontal cracks. In general, damage is damage in the transversal direction. That means this part, the Y direction of the structure, is more prominent than the one in the longitudinal or X direction of the structure. Over the past few decades, several restoration works have been performed on the structure in order to mitigate the presence of damages. Nonetheless, the damage pattern identified due to the incremental gravitational loading are representative of the damages observed in the recorded documents of the building. And we can see in the documents that severe restorations have been placed in the gallery in this part. So it means that in the past, this part has been faced with severe damages. To perform the seismic analysis, pushover analysis was conducted on the numerical models in both longitudinal, means X, and transversal, Y directions, considering positive and negative orientations. Pushover analysis is a nonlinear static analysis carried out under constant gravity loads and monolithically increasing horizontal loads. This analysis accounts for the nonlinear behavior of materials, and the seismic action is simulated through horizontal forces. Pushover analysis allows to determine the capacity of the structure to withstand horizontal loads and is considered a powerful tool for assessing complex unreinforced masonry structures. As you can see in this graph, the capacity curve of the structure is shown, which illustrates the maximum load capacity of the structure reaches to 0.15 G. At this load level, the dome has a minor displacement of 5 millimeters. Minaret number 7 experiences more than 20 centimeter of displacement, which you can see with the red line. And other minarets, I mean the rest of the minarets, this experience about 7 centimeters of displacement. As you can see in this picture, the damage is more pronounced at the base of the minarets, characterized by diagonal and horizontal cracks, while minor damages appear on the main arches in these parts, in the first and second floors. The masonry walls of the dome hall present no damage. Furthermore, no damage is identified on the dome nor in the tomb area. Here and here and in the walls we can see no damages. The failure mechanism is observed in minaret number 7 here. The extent of damage at the base of the minaret number 7 is notably more severe since the structure in this part presents some asymmetry and the wall supporting this minaret is thinner, I mean this wall, compared to the other walls of the octagon, especially in this part. In the first model, since the results in all directions were similar and in all directions failure mechanism observed in minarets, so only results in the positive X direction is presented here. In the second scenario, as I said before, all minarets were removed along with the inside stairs from the model. So we here have the model without the minarets and the stairs inside. And the pushover analysis was performed in all directions. As you can see in this graph, in the negative, as you can see in the graph, compared to the with minaret model, which we had the maximum load capacity of 0.15 G, the load capacity increases in both negative and positive direction, 0.33 G in the positive and 0.72 G in the negative direction. In the negative direction, which is this model, failure occurs in the tomb. As you can see, we have severe damages here. The control point on top of the dome registered a minor displacement of 0.17 millimeters. We can see here at maximum load factor, whereas a point on the uppermost part of the tomb where failure occurs here exceeded the limit displacement of 10 centimeter at the same load factor. In this analysis, the maximum displacement of the structure have been limited to 10 centimeter. So in general, the damage is primarily concentrated within the dome and the north corners in the positive X direction. We can see here the north part of the dome and the north corners are severely damaged in the positive X direction pushover analysis. And in the negative, we can see that the severe damage happens in the tomb part. Cracks predominantly show a characteristic shear diagonal pattern here and here. We can see the diagonal cracks, but vertical cracks are also evident on the dome, as we can see in this picture. These cracks on the dome are extending downward through the transition zone and continuing through the structure over the main arch and going downward. In both models, we can see this, but more severely in the positive X direction because it involves the dome. In the positive and negative Y direction, in the second scenario, the capacity curve shows that the structure presents a maximum load factor of 0.29 G in the positive direction and a slightly higher maximum value up to 0.33 G in the opposite direction, which is again lower than the first scenario where the maximum load factor was 0.15 G. In the Y direction, in the positive Y direction, which is this model or this picture, diagonal meridian cracks are observed on the dome. You can see extending downward through the drum and the transition zone, and ultimately passing through the main arches of the ground and first floor. These diagonal cracks develop in clusters, as you can see. And become more severe in the corners of the dome hull. We can see in the corner the damage are more severe. Additionally, hoop cracks are visible on the dome in different heights. Horizontal cracks are visible in the connection zone of the drum and the roof. Here in this part, in the terrace level, we have the horizontal cracks. And in the tomb area, diagonal and horizontal cracks appear through the small dome of the tomb and the walls here and going downward. Finally, diagonal cracks spreading from the corners or and openings, corners over the openings, as we can see here in these pictures. The result of the analysis in negative direction in this picture reveals a similar damage pattern. Nonetheless, these cracks are less severe in the corners where compared to the positive Y direction. In general, the evaluation of the analysis in the negative Y direction reveals comparatively lesser damage than what observed in the positive Y direction. This discrepancy could be attributed to the observed structural asymmetry and a slight reduction in the thickness of the surrounding walls, particularly noticeable in the third floor, which we saw the effect of this asymmetry also in the second scenario and the result of the model with minarets. And finally, the current configuration of the structure. The objective of this analysis is to assess the seismic behavior of the mausoleum in its current configuration to the fullest extent possible, although we had limited information to include in the model. Regarding the interventions that have been performed in the mausoleum, as I said before, a reinforced concrete ring was built below the base of the dome, somewhere here, but we exactly don't know where is the place of that intervention. In addition, minaret number 2, this minaret here, has been consolidated using steel belts, vertical steel elements, and also cement-based mortar. Unfortunately, detailed data considering design specifications, concrete and steel properties, and other related information were not accessible for inclusion in the finite element model. To account for the effects of the aforementioned interventions and structural changes within the model, the concrete ring and minaret number 2 were represented as elements with fully elastic behavior. So, for the result, in the graph, we can see that the capacity curve of the structure for a point on top of the dome and a point on top of each minaret present that the load capacity of the structure has increased again, and we have maximum load capacity of 0.21 G here with the corresponding maximum displacement of 8 millimeters for the top of the dome, as you can see here. Minaret number 1 and number 3, which is here in the back or in this picture here, both are original and they experience the same displacement as the dome. As you can see also in the graph, the dome and minaret number 1 and number 3 experience the same displacement. Minaret number 7, which is also original, undergoes a displacement of 45 millimeters. This result for minaret number 7 confirms the result from the previous analysis on the model with minarets, indicating that minaret number 7 is susceptible to collapse against lateral loads, irrespective of its different height in the original and current condition model. Minaret number 2 experiences a displacement of 44 millimeter at maximum load factor. This value for displacement can be attributed to the lack of connection between the steel tie and the base, since the consolidation focused solely on the upper part, neglecting the connection between the base of the minaret and the roof. Here. Minaret number 4, 5, 6, and 8, which were reconstructed, experienced displacement of about 80 millimeters at maximum load factor. We can see that the minarets next to these minarets, it means minaret number 1, 3, and 7, have been partially collapsed. So the high displacement in these minarets also can be attributed to the distortion of building geometry and load path in the structure in these sections. This highlights the importance of geometry and design in structures. This shows the interrelation between the theoretical geometry in terms of design and practical geometry in terms of construction techniques in construction of such buildings, which is very important to be aware about and consider it in restoration works. And for conclusion, I would say that in case of application of lateral forces in with minaret and current condition models, which both include the minarets, the original configuration of the mausoleum presents a significantly high safety level for vertical loading, which means 5 times of the self-weight, as we saw. This can be attributed to several factors, including the load-bearing system of the structure, which is called tagh va tavize in Persian, and the considerable thickness of the walls of octagon, which are the main wall of the structure. The initial failure mechanism primarily involves the minarets at base. Although minarets can dissipate the seismic load, they stand out as particularly vulnerable elements in the structure. Thus, The collapse of minarets may potentially damage the dome. Therefore, considering the structural safety of the mausoleum, minarets require careful monitoring and potential retrofitting measures. It is necessary to understand the design and construction logic between the main structure and the secondary structure before any interventions. Minaret number 7 is susceptible to instability at the base regardless of its different heights in the original and current condition model. Original shape of the structure should be retained to balance the load-bearing system and the structural response. Importance of symmetry and original geometry of the structure need to be considered. We saw that in model without minaret, the transversal direction, it means the y direction, is the most vulnerable direction, especially the negative, the positive y. This can be attributed to the asymmetric geometry and lower thickness of the western wall of the dome hall. Compared to the with minaret model, the without minaret model presents higher load capacity and consequently notably higher level of damages. Straightening or removing the minarets will enhance the system's load capacity, as we saw. However, for the sake of authenticity, the minarets should be preserved. For the future work, we suggest development of a diagnostic approach to understand the cause of structural and non-structural damages, which is crucial for refining and validating the assumptions made for the numerical models. Also, the performance of in situ experimental tests to ascertain the actual material properties, dynamic properties, morphological and structural evaluation of the double layer walls and the dome, for example, by using GPR technique, geotechnical tests and surveys, including excavations to assess the foundation, comprehensive structural assessment, taking into account all the structural interventions in the present configuration, and finally, development of a comprehensive restoration and conservation plan based on their findings, considering specific interventions, preservation techniques, material to be used, historical authenticity, and cultural significance of the structure. I suggest you for more detailed information about this project, refer to a paper which has been published in Structure Journal, an article, and where you can find more information, because in the presentation, due to the lack of time, we have to neglect some parts. So you can refer to this article to know more about this project. Thank you very much for your time and attention.
Thank you very much, Arezzo, for this very nice and very comprehensive presentation. It was very interesting to see the usage of Diana for the assessment of historical building. So thanks a lot for that. In the meantime, I was scanning the question box, and there are two questions that are basically on the same topic. For the modeling, did you create the geometry directly in Diana, or you imported the geometry?
Actually, the main geometry was performed in AutoCAD, but I had to transfer between Diana and AutoCAD for several times. But I can say that some parts are also has also been done in Diana, but the main part in AutoCAD.
Because to add on that, there are a few comments who are really pointing the fact that your mesh is really a piece of art. That's really a nice achievement. So basically, that was the two main questions that I get from the audience. The rest is only compliments about the presentation and the outcome of this presentation. So in the name of the audience, I'd like again to thank you for taking the time to give this presentation and also to present what can be done with Diana. So that's really a great work. Let me see if there are more questions coming. Actually there is one more question coming. Did you also perform an RN value analysis on the 3 different model?
Yes, we did.
And then
with Diana, we did.
You did, okay. And to follow up on this question, were the main RN frequencies in the range of the earthquake, so between 0 and 30 Hertz, or not?
Yes, it was. As I remember, the main frequency was 3.2.
Okay, I hope it answers your question, Yona. Thank you for raising this question.
Yes, regarding the eigenvalue, it is explained in the article.
Okay, so people can always refer to the reference of the paper that you shared. So that's very good. So let me see if there are more questions. Okay, so Yona is happy with your answer, and she will look up the article. And again, she joins the rest of the audience, and she thanks you for the great presentation, Arezu. So I think there are no more questions for the time being. As I mentioned in introduction, we have recorded this session. So after processing and review by Arezu, we will decide to publish it in our YouTube channel. So this may take a few days, but so keep an eye on our YouTube channel. And I think we are all happy to have joined this nice session and to see your work on this very nice historical building. In the name of Diana FEA and also of the audience, I'd like to thank you one more time, Arezu, for taking the time of presenting this great work and the great results. Thanks a lot. Really, honestly, it was a very nice presentation.
Thank you so much. I would like to thank you and all the audience. Thank you.
So I'm going to conclude this session. So I'd like to thank all the people who attend this webinar today. So keep an eye on our YouTube channel. This webinar will be available in a few days. And of course, keep an eye on our website. There are more events coming. In 2 weeks' time, we have our introduction webinar. And the week after, there will be the last run of our reinforced concrete course for this year. So don't miss the opportunity to join this course. And of course, there are many more events. So just keep an eye on our website. So I'd like to thank you all for attending this webinar, and I wish you a nice end of the day or nice end of the morning, depending where you are located in the world. Thank you all. Bye.